Hello, can you hear me? Okay, thanks everyone for coming. I was just talking to some people outside. It feels like I'm planning a wedding. Like you plan months in advance, and then you kind of, I mean, I've never planned a wedding, but from what I can, probably it's a bit more work actually. But and then actually when people get here, it's kind of nice to see. I feel like lots of new faces I know very well, and then a bunch of faces that I don't know. So I feel like I'm kind of being introduced to the bride's family. And the other thing is that you plan this thing, and the girl does 90% of the work, and that's more or less what happened here as well. But anyway, let's see. So, but one of the differences though about the wedding is that at the end of the day, you're the one whose show it is, right? But here, I get to sit back and watch you guys give talks. So that's kind of nice, and I'm really looking forward to that because we have a list of some really interesting speakers. So here in Nijmegen, so Mertha's about to tell you about our wonderful group and how it's growing. And one of the things I like the most about the group here is actually the sociology of the group. So the thing that I like is that people are very open, people are supportive, there's always good discussions, and I really enjoy coming to work, and I enjoy coming to the talks and having interactions. And so one of the things that we are trying to create with the conference is that kind of attitude, right? So we wanted to think of people doing interesting work who are going to be constructive, interesting to talk to, and open-minded and whatever. And so that's one of the main themes that we had in our head when we were kind of thinking of a list of speakers. And so, yeah, so I'm really hoping to meet more of you and also get to know a bit more what you do. As far as the topics for the conference, we called it, the title is Shapes of Gravity. And part of that is because there's a bit of a small shape dynamics component, but that was really a small aspect. There's also the fact that there's the role of conformal invariance in quantum gravity, partly due to the fact of the properties of UV fixed points of RG flow, is becoming more and more interesting, and quite a few of the talks here will be talking about conformal invariance in different kinds of conformal invariance in different ways. But really, the conference should maybe be called something like aspects of gravity, because I mean, one of the things that Mercedes was really pushing early in the planning was we want to get different viewpoints and different kind of scenarios for how what could happen as physics gets close to the Planck scale. And so we have many different talks from many different perspectives talking about different ways of doing that. And so it should be aspects of gravity, but shapes of gravity sounded cooler, and Renata suggested it, so we had to say yes. We didn't have choice, yeah. But anyway, I think it's a good title. Okay, so that's more or less all I had to say. So now I'm going to pass over the mic, and hopefully I won't say much more for the rest of the conference.
Yeah. Let me also thank all of you for being here. I am very happy to organize this conference. I must say first that I don't feel like organizing a wedding. This is just a conference. Okay. So, yeah, I will say a few words about this faculty. This is the Faculty of Science of Radboud University. As you see, it's a very new building. It was opened in 2007, I believe. And it hosts many research institutes doing research in many aspects of science: natural science, mathematics, computing science. And, well, among all the institutes, it also hosts our institute, the Institute for Astrophysics, Mathematics, and Particle Physics. And we are formed by 3 departments: Department of Mathematics. We also have one of the biggest groups in astrophysics in the Netherlands. And our Department of High Energy Physics especially works in particle physics. But since 2012, when Professor Renate Lol moved here from Utrecht, we also have one of the biggest quantum gravity groups in the Netherlands. And I would say this is the only group working in non-perturbative approaches to quantum gravity. And it's really a very exciting group because we are very diverse. We work in many different approaches. In particular, we have causal dynamical triangulations that is pushed by Renate and Jan and other people in the group. We also have people working on functional renormalization group approach applied to asymptotic safety scenario for quantum gravity. We have people working on loop quantum gravity and loop quantum cosmology, like myself. We also have people working on spin phones, on group field theory, and topics related to these fields of research. So the group is growing fast, and we hope that this keeps happening. And you are all welcome to come visiting us and also to apply whenever there are available positions, because we often have PhD positions and postdoc positions. Okay, and so I hope you enjoy your time these days in Nijmegen and also at our faculty, and I also hope you enjoy the conference. All right, and I think I won't say more words because otherwise we will be late. So let me now introduce Professor Renate Loll. She's the leader of our group, and she will be chairing the session today, at least in the morning. All right.
Yes, a very warm welcome to all of you. Very excited to have you here. There's still a few people on their way, clearly. So welcome here in Nijmegen at the Radboud University. I'm, as Merci was saying, I'm the CEO of the quantum gravity operation here. But for the purpose of this conference, I stay a little bit in the background and let the show be run by the younger folks who've been very active. I've hardly done any work, so I should emphasize that. So those two, Merci and Sean, and our secretaries have done the bulk of the work so far. So without much ado, let me introduce the first speaker of today, who is Yanam Buren. Jan hardly needs very much of an introduction. He is working mainly at the Niels Bohr Institute at the University of Copenhagen, but he is an affiliate here, so that means in practice that he is here usually one day a week on Fridays to join our seminar and entertain the rest of us. Jan is an expert on many aspects of quantum field theories and gravity, both in the continuum and on the lattice. And well, one of his many strengths is combination of analytical and numerical techniques to arrive at interesting results. So today I'm very pleased to say he'll be talking about quantum gravity, non-perturbative quantum gravity, in particular new results that have been obtained in the approach of causal dynamical triangulations, of which we are one of the champions here. So he's also kindly taken upon him the task of getting us all started and waking us all up. So without much ado, please, Jan, come forward and talk to us about the phases of gravity.
Sure. Yeah, so thank you for being here. Modestly, I changed the title, so it's a little bit grand to call it Phases of Quantum Gravity, because, well, we don't know whether this theory called CDT describes gravity, but this is our task to show whether, well, to prove that this is the case or show that it's not the case. But anyway, it is a theory of quantum geometry, so phases of a quantum theory of geometry is maybe more modest title. So I listed here, let's see. Yeah, that's working, but I wanted the... here, it's in the middle. It's in the middle. Yeah. Okay. Great. Yeah. So I listed some of the collaborators who have participated in creating the data which I will present today. Some new phases of CDT, the causal dynamical triangulations. So let me first say some words of generality here. Well, since this is the first talk, why not? Lattice field theory has been very successful when addressing non-perturbative aspects of quantum field theory. And maybe most spectacular is the calculation of the hadronic spectrum. I mean, I think it cannot be emphasized enough that basically you can write down the Lagrangian of QCD, which involves no coupling constants if you forget about the masses of the quarks, and if you only consider the strong interactions, it involves no coupling constants, basically. You write it down on a piece of paper, and you hand this piece of paper to your ultra-bright student, and then he will go on the computer, and he will produce a series of numbers where the number he associates with the pion, he adjusts to be the mass of the pion, and then basically all the other masses of the hadrons will come out. Well, this is exaggerating a little bit the state of affair, but this is basically what it is. So amazingly successful quantum field theory here. So, but it's well, I would say the ultimate success. I mean, you have no parameters in the theory, and nevertheless, quantum field theory unfolds for you a complex scenario of many masses, resonances, etc., etc. Well, but so, and of course we have a continuum from the start. We have a continuum candidate theory, QCD, and in order to do non-perturbative calculations, well, in principle, if we were clever enough, we could do them on a piece of paper, but we are not, so we put them on a lattice and do Monte Carlo simulations. And although that is cumbersome, it seems to work. But of course, we know this theory. We have a candidate theory, and we know it's renormalizable, it's asymptotically free, and that means that the ultraviolet part of this theory is under control. So that's, of course, very important for being able to extract these data. And kind of underlying this lattice QCD is the Wilsonian view, where the details of the lattice regularization are in principle not important at all. We can start out with basically any lattice Hamiltonian in an infinite dimensional coupling constant space. But it is kind of possible to find our way in this coupling constant space because the critical surfaces where you get infinite distance correlation function on the lattice, they are in general assumed to have finite codimension. So consider a standard magnetic system, adjust the temperature. So this is here, we adjust the temperature. At some critical temperature, we are going, the correlation lengths of these spins are going to be infinite. We are at the critical surface. So there are many magnetic systems. Some where we adjust the temperature will hit it at a different position on this critical surface. But the continuum physics of all this is basically the same. So the critical exponents of these magnetic systems are all the same. And this was mentally explained to us by Ken Wilson by saying that, well, they are in the basin of attraction of a fixed point, such that if you apply the normalization group to these spin systems, you integrate out degrees of freedom, then you will move towards this fixed point. And since the correlation length is already infinite, it doesn't change when you apply the normalization group. It's infinite, and you move to this fixed point, and all physics here is basically the same. So, well, I think, so I see, I made this hand-drawn picture here, well, partly by laziness, but also to illustrate, because I think that is the essence of Ken Wilson's work, that it's still possible to get the Nobel Prize by drawing such a picture. That's encouraging for the rest of us. So, having the correct deep understanding. So symmetries are, of course, important indicators of different fixed points. And they are really very helpful when identifying various critical surfaces and where you are. For instance, if we return to our QCD thing, it is much easier to deal with the lattice gauge series on a lattice if you manage to create a natural concept of gauge invariance on the lattice, which is compatible with what you would expect in the continuum. So now turning to gravity and viewing gravity as a series of geometries, two questions arise. So first of all, what is a natural kind of lattice implementation of such a theory of geometry, in particular with the viewpoint that we want to view it in a quantum field theory. And for the quantum field theory, of course, the next question is, what quantum field theory of geometries do we really want to implement on the lattice? Now, let's think about the first question. And it is maybe best addressed in 2 dimensions, where there is a very simple theory of geometries, which is renormalizable, and which is maximally quantum in terms of fluctuating geometries, and which can be solved explicitly, both on the lattice and in the continuum. So this is a very unique situation. And this is called 2D Euclidean quantum gravity, or Liouville quantum gravity. So this is, of course, one of my pet topics. I will try to constrain myself today. But, of course, I talk about it whenever I get a chance. So since there's nobody to stop me here, I'll spend a few seconds talking about this, because it illustrates some of the points that we want to come to. So so here's the partition function. We are integrating our geometries. We have an action of geometry, which we, in 2D, is very simple if you don't want to sum our different topologies of spacetime. It's because the Einstein term is absent. It's a topological one, so it's just a cosmological term. It's trivial. It has no derivatives. So you can say it's basically not there. But we are still kind of summing our geometries. So in this sense, it is maximally quantum because there is no action. Each geometry has the same weight. So that's formally corresponding to putting h bar to infinity, because h bar is dividing S here. And then we have some matter fields, which couples. We can integrate out the matter fields for a given geometry, and then for the geometry gets some weight depending on the matter field. So how to put this on the lattice? Well, so one can try various things, but what has been very useful is to build up the geometries of equilateral triangles, which you glue together in all possible ways. So such a geometry will be a piecewise linear geometry. So it is a continuous geometry. And of course, in the path integral, so we have, of course, to decide exactly what do we mean by integrating over all geometries here. But most likely, if you think about path integral in all other contexts, I mean, it involves continuous geometries. Maybe geometries which are nowhere differentiable, but are continuous. And certainly the piecewise linear geometries is a subset of this. So the question is it a sufficient subset to capture the measure here, which you can actually calculate in the continuum also? And the answer turns out to be affirmative. So you replace the path integral over geometries by the sum over these triangulations. The action is very easily translated because each triangle, if you give a linked length of A, it is equilateral. It has this area here. So this is the area of the world, and this is a lattice version of it. In dimensionless units, it's just the number of triangles times some coupling constant. So the partition function, which you would like to use on the lattice, is this kind of dimensionless thing, where also we have integrated out the matter field. So we put the, whatever, if it's scalar fields or whatever it is, we put them on the vertices of the triangulation or in the middle of the triangulation. It doesn't matter. Exactly from this Wilsonian point of view, it shouldn't matter too much with the details, and it doesn't. So there is a continuum limit. There is a critical point of this, because the number of triangulations is growing exponentially, and also usually this will add an exponential contribution in NT. So for sufficiently large mu, this is convergent, but it will then diverge at a critical mu. This is a critical point. And this is where you relate to continuum, because you approach this like you are approaching the critical surface. You approach this critical point in this way here, and that fixes NT times the area to be the continuum area here. So that's a nice way to do it. And one can actually kind of capture the matter coupling by attributing different weights to the vertices of the triangulations, or by considering, in addition to triangles, also squares, pentagons, etc., with different weights. So in this way, one has, in a Wilsonian sense, an infinite dimensional coupling constant space. And one has a beautiful realization of the Wilsonian picture with critical surfaces of finite codimension. In fact, if you only take one coupling constant, namely the cosmological coupling constant that I had here, this mu here, So the weight here is then 1 in this sense. Then there is a critical point. It is here. And this corresponds to C equal to 0, quantum gravity without matter. So in the Liouville thing, it's a C equal to 0 kind of theory, where C is the central charge of conformal matter coupled to gravity. So this is already a complicated theory. When you can ask many interesting questions there, but I will not go into that. But now add another coupling constant. Say add squares to the triangles and give them an arbitrary coupling constant. Then you have a two-dimensional coupling constant space, and this critical point, turns into a critical line, and it ends. So exactly this picture I want you to keep in mind. So it ends at a critical point here, and at this end point, the chi-universality class is changed. It's no longer C equal to 0, but it is a conformal theory with central charge minus 22 over 5 at this endpoint. So now add a third, say, pentagons with different weights, and then this critical line turns into a critical surface. So the codimension here is always 1, and this critical point turns into a critical line. So this has codimension 2, and it ends again at a point where now the critical theory changes, and now the central charge is this weird number. I will not tell you how you get these, but this is all well understood both on the lattice and in the continuum. So this is a kind of wonderful kind of realization of this Wilsonian picture. However, unfortunately, all this beauty seems not to translate to dimensions higher than 2. So this dynamical triangulation, as it's also called, in the simplest form, seems not really to work in higher dimensions. At least not if you stick to just the simplest discretized Einstein-Hilbert action. So we have it here. This is the continuum version of this written in Euclidean space. Now, in dynamical triangulations, where you have identical building blocks, and you use the Reggie prescription for how to translate this action into action on a piecewise linear manifold, this becomes exceedingly simple because you're using identical building blocks. So all these angles of curvature and so on, which appear in the Reggie prescription, they just kind of disappear basically, in the sense that it will only depend on the number of vertices in the triangulation and the number of four simplices if we are in 4 dimensions. And this K0 is basically the bare inverse version of G here. And this K4 is related to lambda here, the cosmological constants. So we have these two coupling constants, and the action is exceedingly simple. Of course, I mean, the difference between QCD, the quantum field theory, where we knew we had a continuum theory, and here is that we don't know whether we have a continuum quantum theory corresponding to this action. So this is not renormalizable in G, and it is up to us to argue that we have one. One can use various kind of strategies, and asymptotic safety, the exact renormalization group, which you will hear a lot about, is one. Here we are trying to address it on the lattice and find kind of critical surfaces, critical points where you can take the continuum limit. And then the hope is to prove that you have an ultraviolet fixed point there. That's a different strategy. But of course, just taking this action and starting this out on lattice, I mean, we don't really know whether there's a quantum theory corresponding to this. But there should at least exist, perturbatively, is a theory if one adds higher curvature terms to this theory. I mean, this was already proven many, many years ago by Stella and other people, that if you add such a term here, it basically gives, when you make a perturbative expansion around flat space, you get a first-order derivative coming from R squared rather than a second-order derivative in the Gaussian approximation. And that's sufficient to make it, the theory, kind of renormalizable. But the price you pay is that it is not at all obvious that it is a unitary theory, because such higher derivative terms, theories are usually not unitary. our causal dynamical triangulations, they were invented as an attempt to change this situation in the sense that it can address, to some extent, the unitarity issue, and in the hope that one could get a non-trivial theory just using the Einstein-Hilbert action, but one clearly has to change something compared to just summing over all geometries. And the basic assumption was the existence of a time foliation. So many of you have maybe seen this picture before, but let me flash it anyway. So the way that we build up our piecewise linear geometries is that we assume that we have a spatial slice here, which has a fixed topology. So we do not allow, in the time evolution, we do not allow the topology to change. So usually we assume S3 topology, the simplest topology. But if I have the time, I will tell you about some recent results using the T3, because they are quite surprising, but nice. But anyway, almost for the rest of the talk, I will assume we have S3 here. So we make a triangulation here. So we take a dynamical triangulation here. The geometry of the spatial slice is made out by gluing together equilateral tetrahedra, like this red one I've shown here. Here I cannot really show it in. This is like here. So if you have such a tetrahedra, it is connected to a vertex up here, and it's connected to a vertex down here, as shown on this figure here. But also subsimplices are connected, like a triangle in this triangulation will be connected to a link here, such that in the slab between here, I mean, we really have a 4D simplex. So, and then the class of geometries that we sum over are that we take all possible triangulations of the sphere here, made out of these kind of equilateral things, all possible triangulations of the sphere here, and then we connect two given of these triangulations in all possible ways in the slab in between. So, and then, of course, we stack these slabs on top of each other. So in principle, we can start out in Minkowskian space, and that was part of our main motivation, that we start out with Lorentzian signature, and then this time slicing we would like to relate to a causality requirement, but one can just take it as time slicing. It's a little bit up to the what thing you want to emphasize. But we are distinguishing then between space and time clearly, and so in principle we can take the so all links lying here are space-like, and we now insist that the links here are all time-like, and that the lengths of these are connected in this way here. I mean, this requirement is going to build up a piecewise linear manifold with Lorentzian signature. But we can now make a rotation of alpha in the lower complex plane, and then we get, so it is alpha tends to minus alpha, and then we get an Euclidean signature, and the Garay action will change accordingly, as you would expect when rotating from Euclidean to Minkowskian and back again. And again, you might recall this for the dynamic triangulations where all building blocks were identical. The action was really simple, this Einstein-Hilbert action. Here, it becomes slightly more complicated because we have this as we have introduced by hand this asymmetry between space and time here. But still, it is almost as simple. So you have these two kind of building blocks, this one and this one. These are called N423s and N413. And then there is an alpha dependence. So we capture this in this delta here. So this delta is, in principle, you can calculate it as a function of alpha. So this is some complicated sinh inverse, cosine, and depending on the value of alpha, you can calculate this. But I mean, one should emphasize that this is just the Einstein-Hilbert action which is standing here. I mean, of course, on a lattice, we are completely free, cannot to choose the lengths in the time direction to be equal to the lengths of the links in the space direction, even on a hypercubic lattice. The only thing we have to do in order to have the same continuum theory, so to speak, when we take that space to zero, is that we have to adjust the kinetic term in the time direction according to this. And this is exactly what is done here. So there are two coupling constants here, namely again kappa naught, which is related to the inverse gravitational coupling constant, and kappa 4. So this delta is at this stage not a coupling constant, it's just a parameter. However, since we are doing this path integral non-perturbatively, it turns out that effectively this delta turns out to get the status of a coupling constant. The contribution from the path integral measure is such that it mingles with this alpha in such a way that it's more convenient simply to consider this delta here as an additional coupling constant, and in the end kind of address the question of how does time scale in kind of relation to space. That will be then a dynamical question which we should address when we take the continuum limit. So that's basically the philosophy. So the object that we will study is that we have an initial geometry, a 3 geometry. We have a final 3 geometry separated by this by some proper time t, and we are summing over all path integral. And in Gaussian signature, this is like this. We now rotate to Euclidean signature, and we get an expression like this on the lattice, where we have now these 3 coupling constants. However, in all the computer simulations, really K4 is not will not appear as a genuine coupling constant. So it will not appear in our phase diagram simply because, from a computation point of view, it's convenient to fix the total number of force impulses. So that means, since they are multiplying K4, it means that this is not an effective coupling constant in the theory. We compensate for that by doing simulations for many different volumes. So it is not that we are losing information there, but I mean, the dependence on the cosmological constant has to be kind of reconstructed afterwards. So that's the situation. So the corresponding theory has a Hamiltonian. So how do you extract that? Now, recall from quantum mechanics, you have this thing. This is exactly the object which is described by a path integral with the Hamiltonian here, the path integral from with initial x and final x. So when you have a infinitesimal time, this can be written as delta t times a discretized Lagrangian. So this is the foundation of the path integral, and this relation is exact in the sense that kind of product formula for these operators will tell you that this is a good representation. Similar in a quantum field theory, we get the same, where this Lagrangian now depends on the fields which are space dependent. So the initial and final value of these fields appear because we have a derivative here. This is why these appear, as you might recall, when you construct the path integral. So in the case of a hypercubic lattice, delta t cannot be arbitrarily small. It is equal to the lattice spacing in the time direction. And the corresponding object here, when delta t is equal to a, is called the transfer matrix. And in a way, it's defined as a path integral over a slab in between here, where fields might or might not live, depending on your field theory. But it is used to define the Hamiltonian, because we don't have infinitesimal t here. T is discrete, so you have to define what you mean by the Hamiltonian. So you use this to define the Hamiltonian. In the case of gauge series, the path integral will involve integration over time-like links, connecting the two space-like slices. And in the case of CDT, it involves the summation over intermediate 4 geometries, where the 3 geometries at t and t plus a, they are fixed. So basically, M, we call M the transfer matrix, is defined in this way. And of course, if you raise this to the power n, then you get the propagator I talked about before of a spatial geometry for n plus 1 spatial slices up in the triangulation. So all information of the theory is basically contained in this M. It turns out that we will use in confused simulations. We either use Monte Carlo simulations of the full 4D world with a given time extent, or we consider only a one time slab to determine the transfer matrix. It turns out to be useful sometimes. And we have now effectively 2 coupling constants, kappa naught, and this parameter delta, which now is kind of promoted to a coupling constant. So So before turning to the phase diagram, let us take a Wilsonian view on the situation. So we have now created a lattice system where we have maintained diffeomorphism in the spatial directions, in the sense that we are using dynamical triangulations which do not kind of distinguish between any space directions or something like that. But of course, time is singled out. So one can say from a Wilsonian point of view, where symmetry is an important guide to how the continuum will arise, then it is the natural continuum limit, if it exists, is that of kind of projective Hydronic quantum gravity, if that exists. And here I should say one difference in philosophy. So of course we invented. So you can say that our CDT. This is an explicit lattice realization of the ideas of Hutjava, but of course we invented this before Peter. But our philosophy was, and still is, a little bit different. I mean, it's not that we are deadly interested in Hutjava-Lipschitz gravity. Well, it's interesting, but so in Hutjava-Lipschitz gravity, one adds by hand higher derivative spatial terms in order to make the theory renormalizable. So one breaks very explicitly. I mean, we have only broken rather implicitly by considering a special class of triangulations, the symmetry between space and time. But here, by adding these high derivative terms, it's very likely that space and time will scale differently at a possible UV fixed point, as discussed by Peter Hutjava. So of course he never really only discussed kind of the mean field classical aspects of this, and they were the full quantum theory. But his philosophy, it was of course that, well, it's difficult to understand GR because it's not renormalizable. So he was willing to sacrifice the relation between space and time, the simple relation between space and time you think exists in GR. But by ensuring that you only keep second order derivatives in the time direction, and in this way you can have unitarity. So we only use the Einstein-Hilbert action. So our theory in this sense is non-renormalizable. And then a possible UV fixed point might still be one where space and time scales in the same way as one naively would expect from DR. But it's also possible that we have a critical line. So this is why I wanted you to pay attention to this picture that I draw for 2D with a critical line ending in a point which is different. So it's possible that we can have a critical line, and only at the end point of the line, space and time will have the same scaling. So this is all logical possibilities from the general kind of Wilsonian kind of point of view. But I should say that one thing that we presumably have in our theory, and where this was also one motivation from Peter, this is that we have unitarity, because we have this Hamiltonian, lattice Hamiltonian, and formally it satisfies the requirement of, so you can ask in a lattice field theory, you can ask what can you impose some conditions on this Hamiltonian such that the resulting theory will be a unitary theory, and kind of reflection positive, that the Hamiltonian is reflection positive is one requirement you can impose. And what we can prove is that in CDT you have kind of similar properties of this Hamiltonian. It has what one could call kind of reflection positivity. So most likely whatever theory you get out there, if it exists in the continuum, it will correspond to a kind of unitary theory. So here's the phase diagram now for the theory. So at the moment, please forget about this thing here, which is what I will talk about in a second, but please forget about it. I call it the bifurcation. So in this sense, we have three phases, C, A, and B. And we have a phase transition line here, and we have a phase transition line here, and here. So it turns out that this phase transition line is first order, so it's not interesting for continuum physics, but this line seems to be second order, so we were very interested in this line, that it seems also to end. So you have a scenario which looks very similar to what I want to advocate, that here you have some continuum physics coming out, and maybe it has some scaling here, and a different scaling here, and this triple point was exactly like in the Lifshitz phase diagram of magnetic systems. That was so here in magnetic systems you have a anomalous scaling, but here along this line you have ordinary scaling. So it was situation was very interesting from this point of view. So configurations here seemingly do not relate to any continuum physics, and similar here. But here they were, in a tantalizing way, kind of relating to continuum physics. So I'll just so time is here, and the profile that you see here is just the spatial volume and a given time slice. So in phase A, which are not related to continuum physics, I mean, seemingly, the universe splits up in many small disconnected parts, which has no relation to each other. So we didn't want, here we didn't think this was interesting for anything. In phase B, everything collapsed to a single slice, where all the spatial volume was here on a single slice. So it was a kind of dimensional reduction. But the geometry of this spatial slice was not also very appealing. So we didn't want to associate this with any continuum physics. But in phase C, we call it the extended de Sitter phase, things were quite interesting. So you have the time direction here, and it seems that whatever we did, however we started out with these things, they organize itself kind of dynamically in configurations which look like this, where you have a extension of time here, an extension of space here, and they actually scale as you would expect. So remember that we keep n, the total volume, fixed. So the extension here, it scales like n to 1/4. So this is exactly what you would expect from dimensional reasons if this was to considered as time. And then, of course, this scales as n to 3/4, as you would expect space to scale as a function of the total 4 volume. But not only that, the scaling was kind of spectacular. So, of course, the kind of individual configuration, it looks like this. So not so nice. But if you took a couple of millions of these guys and superimposed them, then it turns out that you got a very nice curve here which had a perfect fit to cosine cube. So this is the time here, and this is the spatial volume. So it fitted exactly cosine cube to the time. And so this is valid for all n's. So it scales like this. This is why I say time scales like n to the 4th. So for all n, you could superimpose these curves. And when n was sufficiently large and larger than that, you could superimpose them perfectly into one curve. So this is what is in statistical mechanics is called finite size scaling. So there was a perfect finite size scaling to something like this. So this could all be explained by assuming a mini superspace model like this. So the kind of discretized version of this, it is this, and we could even determine that if you only look at the spatial volume as your observable, then just by not imposing any mini superspace action, but simply studying the 3 volume to 3 volume kind of correlations, you could extract this as the effective action. So this mini superspace action here, so this is not really a cosmological constant standing here. It is just a Lagrange multiplier because in all the simulations we keep the integral of V3 to be fixed. But this term here is of course just the curvature term, and this is a kind of kinetic term. So this is just the mini superspace action of Hartle and Hawking, and of course we know it has as a solution S4 for a given cosmological constant, or if you fix the 4 volume. And that's exactly what we see here. So this cosine cube can be viewed as S4 if we scale time with some suitable S. And one can even relate, so this was what we did, one can relate this gravitational coupling constant to this coupling constant which we can measure. And so you see that G divided by A cube is now just a number, and A is the lattice spacing. So we could, and the square root of G is then the Planck length. So we could say that actually the Planck length corresponded to approximately 1/2 of the lattice spacing. So that was the situation, and we then wanted to study the transition to the second order line here. Because this was where the continuum ultraviolet fixed point could hopefully be found. And we put a lot of effort into making these studies. They were not happy studies in the sense that we didn't find the fixed point that we wanted along this line. But now it is also, now we understand that this is because, well, not because, but one reason is that they actually separated the phase C, where all these nice properties doesn't extend all the way down to here. There is what's called a bifurcation phase, which are separating them. And also in this bifurcation phase, it turns out that one probably would not attribute any continuum physics. However, so this is preliminary results, which have not really been published yet, but it turns out that this is also a second order phase transition. So it is kind of remarkable. You have this unbelievably rich phase diagram with this very simple action that you put in. Only you have these two coupling constants to adjust, and it creates this amazing picture. But that's what it is. So we discovered this bifurcation phase by studying the transfer matrix. So here is the transfer matrix where I have truncated. So before there was a 3 geometry, a triangulation here and a triangulation here, but now I have truncated it only to relate to the 3 volume here and the 3 volume here at 2 neighboring time slices. And you can measure this, and to a very good approximation, it is given by this, as it should, because I just told you that kind of this thing here. This is the discretized action which describes the whole thing. And I also told you earlier that the transfer matrix is exactly related to the action. And this is what you see here. So we can actually measure this with this constant here, and 1/3 comes out quite well. So we have a potential term here, and you can say a kinetic term here. However, it turns out that in the bifurcation phase and in phase B, this kinetic term, this just gives a Gaussian peak saying that 2 neighboring slices, they want to have the same volume, basically. But it turns out that in the bifurcation phase, it separates into a double peak situation. And, well, that was how we discovered it, because we wanted to understand how did the transfer matrix look in phase B. And in phase B, we have one slice with a very large volume, and the next one has very small volume. So clearly, the term could not be like this. In fact, it is like this, but then we realized that this continued all the way when we crossed the BC phase transition. So here I have plotted the transfer matrix for various values of delta. So the phase diagram, oops. So I remind you about the phase diagram here. So we go down here, we start out in phase C, then we go down here, decreasing delta. And then what you see is that you start out in phase C with a nice peak like this. So this is a Gaussian kinetic term. But then when delta is decreasing, it separates into things like this here. So there's a double peak structure. So you could ask, okay, so let me go here. So this double peak structure, it suggests that in neighboring slices, the spatial volume, or say the number of vertices, are not really the same. They change kind of slightly. And it turns out that there is seemingly built in an antiferromagnetic structure with oscillating number of vertices. And this is all governed by a single vertex in every second slice of high coordination number. So here's this vertex of high coordination number. It connects then to a number of vertices on the next slice where there's no vertex of high coordination number, but which are then again connected like this. Of course, a priori, there didn't need to be any causal relation between these. It could be a situation like this, but this is not what happens. So you should imagine here that here's time, and there's a lot of stuff here, triangulation out here in space, but there's one vertex of high order which forms a kind of substructure into this. and which similarly ties the whole thing together. So in phase C, it is not present. I mean, phase C is homogeneous in space. And this phase transition between the phase C and the bifurcation phase can be viewed as a spontaneous breaking of translation of homogeneity in space. So this is similarly what happens. And this is then related similarly to a kind of second order transition. So a possible order parameter that we were using was the highest order of a vertex in one slice and the next, the difference here. And you see that in phase C, that it's just a flat curve being quite small number. But then it increases when you go towards phase B. And in the end, these high vertices, they eat up everything. And in phase B, they are just connected to everything. So it's a spider web there determined by one vertex. So you can say, how could we have missed that when we first looked at it? So I should excuse myself. So how could we? So it turns out, well, so it's kind of interesting. So you have to realize that what we see on the computer is some kind of blob. Well, I mean, it has huge fluctuations and so on. So only when we superimpose a couple of millions of these guys, we see this nice cosine cube curve. But here's an interesting question. I mean, so this is supposed to be the universe, and now we are superimposing various universes. Well, I challenge you to think about this concept, you know, but this is what we have to do in order to get some structure out. So what we actually did, it was that we took a vertex corresponding to a relatively large spatial volume, and we put it on top of the neighboring one, which also has some of the largest volume there, and then we make the superposition. But this blob structure is fluctuating, and also it is translating along time direction. So we have used periodic time, so it is translating. So if you just look at a single point there, I mean, if you average over a couple of millions without doing these translations of the blob, then you will just see a uniform distribution, because there's translation invariance of this. So you have to make this translation. But this translation, if you just do it with some procedure, you can easily blur the fact that in the neighboring slice there are slightly less volume than the other ones, because you have to make some procedure for translating them, and if this mixes these things, you will see a smooth curve, and this is exactly what I'm showing here. So here's a real thing from phase C, and here's a thing from the bifurcation phase. So this is a 3-volume measured with our procedure, and you don't see this structure because it's averaged out. So everything looked, so this is why we didn't see it originally. Only when we looked at the transfer matrix coming from phase B, we realized that there was this structure. But this is, of course, very important. So there is now this new second-order transition, and it can be viewed, as I said, as a breaking of spatial homogeneity by this single vertex. And now, since we want to approach this thing from phase B, now a possible UV fixed point should be found along this line. So prior to this, we wasted a lot of time, or not wasted, because now the procedure is kind of formulated. We looked for a UV fixed point, and it can be found by following the flow of bare coupling constants when you keep continuum physics fixed. This is a standard procedure from lattice gauge series or lattice field series. Of course, you have to define what you mean by continuum physics and keep it fixed. And then it turns out that it's actually easier to find UV fixed points than infrared fixed points with this procedure. You naturally flow to a UV fixed point. But we were looking at it at the wrong place, so that was why we probably didn't find it. So we have to restart this program now to look for UV fixed point along the new line. And this is potentially, I mean, in my view, this is very good news, actually, for the prospect of finding a UV fixed point which is related to GR and not to Hydronic gravity. So I said, as generically, you would expect Hydronic gravity because we are breaking this thing, but this breaking is quite mild, you know. So you can also break many things on the lattice which are restored at the fixed point because of scale invariance and all kinds of other things. At this, but the old B transition looked very asymmetric between space and time, because in phase B, time has basically disappeared. So it smelled very much like Hochschild-Lifshitz way of thinking about this, where time scales differently from space, and in order to get a continuum limit, you really have to scale them differently. But along the new line, space and time really scales in the same way. So if there is a UV fixed point there, it's most likely kind of related to GR, at least there's a chance that it's related to GR, than to Hochschild-Lifshitz gravity. So that is good news. So that's basically the summary of what I want to tell you, that we are now entering a very interesting phase in CDC. We are now looking for a new fixed point, which has a great chance of being kind of related to GR and maybe to the GR fixed points which are seen by asymptotic safety. So that's exciting news. Added bonus thing I cannot tell you because our chairperson here will kick me away, but I will still do it. So just to tell you, so we studied CDT also with space topology T3 rather than S3. So here's a transfer matrix with the topology S3. So this term was related to a classical gravity term, namely the spatial curvature term of S3. And that was why we found the S4 solution, the cosine cube thing. On the torus, on the other hand, this is flat. And so we don't have this term here. Well, it's not needed. In fact, this is kind of zero. But we find another term, which is actually different by 1 power here, in this case here. And this term is very interesting because, well, the origin of this is clearly completely quantum. I mean, there's no classical term here. It must be higher order kind of correction. So it's purely quantum. We were looking for such terms also here, but we couldn't see them in noise coming from basically from this term here. But here this term is absent, and we can identify this term here, and you can also view this as an effective classical action or semi-classical action, and you can solve the continuum version of this, and this is just flat space. So everything is fluctuating. So we don't have these blobs any longer. It's just fluctuating around flat space, as one would expect in the case of the torus. So this is also very nice point of view. First of all, we can determine the quantum fluctuations, and next, the semi-classical logic of these mini superspace actions, they seem to work. So I will shut up now. Thank you very much. Yeah.
Thanks, Yanam, very much for this warm-up. Are there any questions?
Didn't Bujava also had something like an oscillating phase in this mean field discussion?
Well, Kaihutjava has many phases because he's adding a lot of terms to this. So we are only having the So it's a little bit difficult to directly compare. But of course, as I said, in general, of course, the regularization are of course exactly like Kaihutjava, but by hand we are only adding the Einstein-Hilbert action. But effectively, other terms pop up. Yeah. No. Sure. That's why I say that if you take a Wilsonian point of view, you would say that by default you would end up in the Hochschild-Lifshitz scenario, but it could be different. I mean, at special points, it could be different. No. Sure. Yeah. So we haven't seen oscillate. Well, so the phase A. It cannot really be called oscillating. It's basically disconnected. So we haven't seen this oscillating phase. Yeah. We haven't seen it.
When you showed this renewed CDT phase diagram, you extrapolated to quadruple.
Yeah, that's that. No. I mean, we cannot see that to claim that they meet in one point is just a joke, basically. Yeah. I mean, we don't know.
Thanks for the clarification.
Yeah.
So, but in order to compare with the Hochschild-Lifshitz in the continuum limit, wouldn't you need also to remove the dependence on the proper time to really check that you get the GR integral, not something depending on a slicing?
Well, not necessarily. I mean, if you take kind of Hydronic projective kind of gravity, I mean, you can fix the gauge to be proper time gauge. Well, that's in fact a physical observable in Hydronic gravity, proper time gauge. So, if we are claiming that these are geometries, they do not refer to coordinates, then it would be natural to associate this with proper time. And in this sense, time is a real physical thing. But I mean, you can make various but this time, of course, in Hydronic, this is just a coordinate. Huh? If we claim that this is a geometry, it is not a coordinate. But the actual interpretation of this, as I said, I mean, so we have, well, so we have tried to kind of check, made various checks about how this parameter alpha kind of relates to what you would think was the physical signals, and it doesn't relate very closely. And that's why we are saying that in this sense we don't really, you will have to see the end result to judge what you can, how to interpret the time extent, you know. And does it scale in the same way as space? If it scales differently, you would like to relate it to one of the ultraviolet fixed points of Hydronic. But if it doesn't, yeah, then it doesn't, and then probably it's just some kind of proper time. But I mean, there's some leverage for interpretations for sure, absolutely. Yeah.
I'm afraid we should stop here, continue discussion over coffee, and we meet here again at 10 to 11. So thank you very much.
Okay, so thanks very much. It's a great pleasure for me to be here today. So I'm going to talk about Lorentz violations, causality, and black holes. And you know, usually people start this talk trying to justify why they would consider Lorentz violations, because Lorentz symmetry is a very fundamental symmetry for theoretical physics. And usually people might give arguments that have to do with why Lorentz symmetry might not be fundamental in quantum gravity, or why we want to test the fundamental symmetry and so on. But let's set all this aside for a moment, because when one starts talking about black holes, Lorentz symmetry is a very, very special symmetry, right in the very heart of the definition of a black hole, right? So it's an interesting question in its own right, what would happen to the concept of a black hole, to the notion of a black hole, if I were to give up Lorentz symmetry. So let me try to elaborate on that. So, you know, we all know that the causal structure of general relativity is global, but its local counterpart is special relativity. And the cornerstone of the causal structure of special relativity is the light cone. So I have an event, P, and there is a future light cone, which is a set of events that are actually in the future of P. There is a past light cone, the set of events in the past of P. And of course, there is this set of events outside the light cones, which are not causally connected to P. And we attribute this causal structure to Lorentz symmetry. So one can start thinking, okay, if I depart from Lorentz symmetry, how will this causal structure change? And one thing you could do to violate Lorentz symmetry could be to assume that there is a preferred observer. So assume that there is some special frame, right, in which is preferred with respect to the rest of the frames. And in this frame, assume that all of your perturbations, which carry information with them, actually have linear dispersion relations, like this one. So they all have dispersion relation like this one, with different coefficients, with different constants sitting there. So they travel at different speeds, right? But by virtue of this assumption, they all travel at a maximum speed, and the speed doesn't change with wavelength, right? So if I make this assumption, even though I've given up Lorentz symmetry by introducing a preferred observer, there's still going to be these kind of cones for each and every one of my modes. It's just that each cone is going to have a different opening angle. if I have a fastest propagating mode, it will have a wider light cone, a propagation cone. If I have a slower mode, it will have a narrower cone, right? But there'll still be cones, and that's already somewhat, surprising perhaps that this causal structure not exactly so intimately related to Lorentz symmetry as it is to linear dispersions, right? So I'll call this causal structure quasi-relativistic because it's almost right relativity. If I were to consider only the widest light cone, I would tend to think that the causal structure is the same as in special relativity, right? And I'm not coming up with this myself. We have theories of that type, actually gravity theories of that type, and a characteristic example is Einstein ether theory, which is actually general relativity plus a vector field, U, which we call the ether. And the action is constructed to contains all terms quadratic in the first derivatives of U. So these are the terms here. And it has 4 coupling constants, C1 to C4, for all the possible combination. And the special feature of the theory is that U is forced to satisfy this constraint. So U is a unit time-like vector. And that means that essentially it never vanishes. So even if I go to flat space in a local frame, as we would do in general relativity, the vector will not disappear. It will just have unit length, and it will be pointing in a time-like direction, exactly like a preferred observer, right? So it acts, so essentially defines a preferred observer. And that theory was put together precisely as an effective theory, sort of say, that break Lorentz symmetry. It actually breaks the boost part of the Lorentz group and introduces a preferred frame, and you can use it to obtain quantitative constraints on how much Lorentz symmetry breaking could afford in gravity. You can compare with observations. The constraint is C1 to C4. So people have indeed done that, and there is still a sort of a viable corner of this 4-dimensional parameter space. The theory propagates the usual spin to graviton. It has a spin 1 mode, a vector mode, and also a scalar mode, because of course the vector field is not a gauge field. And it has linear dispersion relations around flat space, exactly as I was discussing before. So it has different modes traveling at different speeds. The speeds of each mode are controlled by the choice of couplings that I will make. And if I wanted I could couple matter in a sort of conventional way. I just take the metric with which I wrote this Ricci tensor. I couple it minimally to matter. I don't allow matter to couple to U, to the ether. And then matter light will propagate in the usual light cones of that metric, right? Whereas the other speeds, the other modes that I discussed will have different speeds. Effectively, each of these modes propagate in a different effective metric. They propagate along the null cones of a different effective metric, right? So then you can start asking yourself the question, okay, what will happen to black holes, right? Obviously, if I have some perturbation that propagates faster than light, I cannot go and consider the usual horizons as horizons of a black hole, because I know that they have perturbations that can actually penetrate them in both directions. And indeed, when you start thinking of a black hole in this setting, you should be thinking about it as a solution with multiple horizons, one for each of these modes, essentially. These horizons are precisely, at least in a stationary setting, the killing horizons of these effective metrics in which these modes propagate, right? So the notion of a black hole doesn't, precisely because of this quasi-relativistic structure of this theory, causal structure of this kind of theories, the notion of a black hole is not really threatened. It just needs to be slightly generalized. And instead of having only one horizon, I have multiple horizons sitting at different locations. Right? And you can understand that very simply from a good old space-time diagram where you start thinking of this propagation cones, and you understand the horizon as the point where the future propagation cones have tilted enough so that you can only move inwards if you're moving towards the future. And if you have 2 types or 3 types of propagation cones with different opening angles, obviously, the wider ones would have to tilt a little bit more to have only ingoing motion. So you'd have to be a bit further in. If you have a narrower propagation cone, less tilting would still achieve the desired effect. And that's precisely what is happening. But of course, all of this is a discussion about a specific way to break Lorentz symmetry, which is I introduce a preferred observer, and I continue to have linear dispersions. Once I change the dispersions, which is something I can do when I don't have Lorentz symmetry, and I introduce a dispersion relation like this, for instance, then things change a lot more drastically. And the point is, the moment I turn on this kind of higher order correction to the dispersion relation, I don't have a maximal speed of propagation as I had in a linear dispersion relation. If I choose a large enough k, I can reach a desired speed up to essentially infinite speed. As long as I'm willing to look at higher and higher k, I can get higher and higher speeds. So effectively, I have infinite propagation at high enough momentum. And that is essentially a qualitative difference in the causal structure. It's not just I'm making the light cone a little bit wider. I'm actually making propagation cones disappear. And I'm getting this kind of pre-relativistic causal structure where I have a point P, and there is a surface of simultaneity, right, which are the events that happen at the same time as P. And everything that is in the north of that is in the future, and everything that is in the south of that is in the past. Right? And obviously, when I do this, I don't really have a space-time anymore. I just have sheets of space, that pile up, and are surface of simultaneity means essentially that they're surface of constant time, and they build up a space-time. And indeed, I cannot actually write meaningfully such a dispersion relation if I don't have a preferred foliation. Because if I could mix time and space, I could actually make such a coordinate change, and I could introduce omega to the fourth in this dispersion relation, which would stop making sense as a sensible theory. Right? So once I make this change, I actually change the causal structure very drastically. And of course, an interesting feature is what happens when I make this A parameter here very, very small. You should already have guessed that there is some sort of discontinuity happening there, because if I make A arbitrarily small, I can still get infinite speeds going if I'm willing to go to large enough Ks, whereas for A exactly 0, I just get this light cone structure. So obviously, no experiment can really tell me that A is 0. Right? It can just tell me that it's 0 to some precision. So that's an interesting question. What is happening near that region? Right? Does having black holes somehow means that A is 0? Right? Because obviously it's hard to think what a black hole is in this setting. High enough energies could penetrate any type of horizon I could define in a conventional way. And again, there is a theory that looks like that. And Jan already mentioned in his talk. So I'm going to arrive to it through a different route, through the theory I've already discussed. So suppose you start with the theory I discussed before, Einstein ether theory. As I said, it's a general relativity plus a vector field. Now assume that you want to impose to this vector field an additional constraint, and that constraint is that the vector is hypersurface orthogonal. So if it's hypersurface orthogonal, then you can always write it as a normalized gradient of some scalar, right? Because it's orthogonal to a hypersurface. And because it's unit, actually, that fixes the normalization. So I've introduced here a scalar field, conveniently called it T, and I assume that U is given in this way in terms of T, where I've absorbed the unit time-like constraint in it. And I'm imposing that before any variation and so on and so forth. So that's not just an assumption on a solution. That's just a different theory, right? And once I've done that, because U is time-like, then that means actually that the gradient of T is also time-like. And that means that T is actually a good time coordinate. I could decide to give up part of my gates freedom, choose T as my time, and rewrite everything in a 3+1 splitting, essentially in a foliation by T equals constant surfaces. And then, if I do that, then U takes this form, where this delta is a Kronecker delta, and N is the lapse of the foliation I just introduced. And Kij is the extrinsic curvature of the leaves of that foliation. H is the induced metric. And the action I had before takes this form, this AI is just the gradient of the logarithm of the labs, and this lambda, psi, and eta are just parameters which are related to the parameters that I had before. And this C14 or C13 means C1 plus C3 or C1 plus C4. So the reason I did this little exercise is that this action that I just wrote is nothing but the low energy limit of Horava gravity that Jan mentioned before. So that's the full blown Horava gravity. So L2 is the action I just showed. And the full version contains also a set of operators, L4 and L6, suppressed by suitable powers of a mass scale, which are all the terms you can write that respect the symmetry of that lower order action with 4 and 6 spatial derivatives respectively. So let me explain that a little bit better. What did I do here? I took a diffeomorphism invariant theory. I used part of my diffeos to fix time, essentially to introduce a foliation. So I have the residual symmetry, which is diffeomorphisms that respect this foliation, right? And with this symmetry, I can construct any possible term that has 4 and 6 spatial derivatives and no time derivatives. And this is how I build up this term. There is a large number of these terms. I'm not going to get into the details of these terms because they're not going to be particularly interesting to me. But the point is that these terms obviously change the dispersion relations. They introduce this higher order dispersion relations, 6th order instead of just 4th order that I was considering before. They precisely for this reason, they actually modify the propagator in the UV, and they make the theory arguably power counting normalizable. So that was the initial motivation by Hosava. Here, I'm not going to be interested so much in the quantum properties of the theory. I'm actually just going to be discussing it. I'm discussing it because of its causal structure at the classical level. So in principle, this theory is still infrared viable for suitable choices of psi, lambda, and eta. And its low energy limit is similar to Einstein ether theory. It's not actually Einstein ether theory because I had this hypersurface orthogonality constraint that I added, right? And it is a very good candidate of a theory for what I want to do, which is understand what happens to black holes in this kind of scenario. So, based on my naive understanding, this is a theory where you couldn't define a black hole in a conventional setting. And I have to say that the way I introduced it was chosen precisely because it shows you that if you follow it backwards, you can actually write the whole theory in a covariant manner in terms of a scalar field T and a 4-metric G mu nu. Okay? So you could think of it as a fully covariant or diffeomorphism invariant theory with a metric and a scalar, where the scalar always has a non-trivial configuration that defines a preferred foliation. Okay. Now that we have our theories, we can we can go solve equations and actually see what happens to black holes, and that's what we did. We chose initially we chose the simplest setting, so static, spherical, symmetric solutions. Obviously, since we're not exactly sure what a black hole is yet, we went the easy way, said, okay, let's find some solutions that are black holes in GR, in the sort of GR definition. They have killing horizons, right? And see what are the rest of their properties, right? And indeed, we solved for these solutions. Spherically symmetric solutions are special in this setting because spherically symmetric vectors are actually hypersurface orthogonal. So the solutions of the first theory, which has this vector field, the ether, and the solutions of the second theory will actually match, right? The ether is going to be hypersurface orthogonal. So let me go back. The ether in Einstein ether theory in a spherical symmetric setting will be hypersurface orthogonal. So this constraint is going to be sort of automatically satisfied whether I impose it or not. That doesn't necessarily mean actually, that means that the solutions of Einstein ether theory will be solutions of Horava gravity. That doesn't necessarily mean that Horava gravity doesn't have more solutions because I'm imposing this before the variation, right? But you can, with a little bit of work, you can prove that for asymptotically flat solutions, that is also true, right? It's not trivial, but it can be proven. So these are, and yeah, what I should say is that what we did is that we neglected these terms for the moment, in the sense of saying, oh, look, this will become important at some curvature, but if you're looking at far enough from the singularity, essentially the curvature is not going to be nearly large enough for suitable choice of M star to actually affect the geometry. So, on the other hand, what you do know that these terms do is they actually make your perturbations propagate infinitely fast if you pump enough energy into them. So you know that the causal structure of the theory is actually defined by the foliation and not by the metric. Right? So the surprising feature of these solutions that we found were very, very similar in terms of the metric to the Schwarzschild solution, at least far away from the singularity, to the level that they wouldn't even be distinguishable from the Schwarzschild solution observationally for viable values of the parameters. But they had a very exciting feature, and this has to do with the configuration of the foliation. So what I've done here is that this is a cartoon space-time diagram of such, of one of these solutions, where this dotted line or dashed line is the usual Killing horizon, right, sitting at a constant radius, obviously, and then the colored lines are actually leaves of the preferred foliation. Now, what I have to emphasize is these are surfaces of constant preferred time, right? And since this is preferred time, I can't change it. I can't just make coordinate transformation and use a different preferred time. That's just, I'm stuck with it. Right? So these are special surfaces, and they behave in the way I've shown here. I've color coded them in a way that they get darker green as I go to the future. Right? In the direction of the future, they get darker green. So let's start thinking a little bit what would happen if I'm, say, at this point here, and I try to emit a perturbation. And suppose that this excitation can travel infinitely fast, right? What is my causal constraint? My causal constraint is that it just has to travel towards the future, which means I have to find it after, say, time delta t at the next leaf of the foliation, which is darker, not lighter green, right? So, which pretty much means I could find it anywhere in that region here, because obviously the darker green surfaces start span the whole region, the whole right part of the diagram, right? And obviously I could introduce more and more surfaces, right? I mean, in between the ones I've drawn. But there is this, they all seem to asymptote at what is an R equal constant surface, which is the leaf of the foliation itself. So that is a very special leaf, this red line, right? And it's special because if I were trying to do the same game, to play the same game from a point left of that leaf, say here, I try to emit a perturbation, I'm going to find it after time delta t on a darker green surface, but the darker green surfaces exist only if I go further left. Right? So that red surface, that constant R surface here, that leaf of the foliation is essentially a boundary on this space-time, where if I try to emit any signal, any perturbation left of that boundary, I cannot actually find it to the right, because all of the future of that leaf lies in this direction. And this is precisely because of this simple heuristic picture I drew initially. This is a surface of simultaneity. The future is in this direction, right? And this surface doesn't actually extend to spatial infinity, which is here. It doesn't reach spatial infinity. So it blocks out part of the space-time by the mere assumption that I just have to travel in the future without imposing any finiteness of speed on my excitations or anything like that. So that's kind of a new type of horizon in this kind of theories. And the surprising feature is, when I first thought about these things, I thought, oh, look, if you have this surface of simultaneity, the causal structure is extremely simple. It's practically trivial, right? And that's true in flat space. If I take flat space and I say, okay, let me foliate it in a preferred way, it's done. There's not much I can do. But if I'm actually allowing the foliation to curve, I can get these funny things. And this is essentially a new type of black hole, which, as I said, the whole causal structure is actually defined by the foliation and not by the metric at all. Now, this is essentially the same space-time diagram, but in a fancier form, in a Penrose diagram. So the same results were obtained by Diego Blas and Sergei Sibiriakov in what is the decoupling limit. So essentially, they just neglected how the scalar field T that defines the foliation back reaction of the space-time, and they just looked about how would T configure itself on a Schwarzschild space-time if I solved at that limit, if I just neglected back reaction. And these are just, the curved lines are just the foliation surfaces on a Schwarzschild space-time, and you already see that dark line is precisely this universal horizon. Yes?
Thomas, can you go back to the previous slides? It looks like there's an inner universal horizon.
There is,
What
good.
is the scale?
So this outer one, so as you see, I've sort of neglected that sort of very inner region. There is actually, there can actually be a lot of them. It can be, a whole array of them, and that of course depends. I could actually tune the couplings in such a way that there is only one, or I could have multiple ones. Of course, only the outer one is sort of relevant for that region, and only one has this asymptotic region. These ones do not. This region of the diagram is not the asymptotic region. This one here is practically very close to the usual horizon. So for a sizable black hole, is at large distances, at large separations from the singularity, and I don't expect the terms I neglected in the action to actually modify the geometry or the foliation drastically at that scale. And as I go further in, I could have, of course, that's why I suppressed this part of the diagram, because, of course, I don't trust it anymore. If I include the higher order correction of Horava gravity, I don't know what is happening there. But I'm happy to find this kind of structure already at a distance which is very, very large. It could be orders of magnitude, larger than the characteristic length scale that suppresses the higher order operators. So this is all in spherical symmetry. Somebody could tell me, okay, that's way too much symmetry, and you already told us that the two theories have the same solutions when you impose spherical symmetry, so that's clearly a special case. So the first thing we did is, of course, we tried to look for rotating black holes, which are not spherically symmetric, and what we found is, first of all, in Einstein ether theory, once you give up spherical symmetry, the ether has two choices, essentially, right? It doesn't have to be spherically symmetric anymore. So when you try to solve the equations, it could either, choose to be spherically symmetric, and you could find solutions where the ether is accidentally spherically symmetric and defines the foliation, right? Or it could just choose to develop vorticity, and then it wouldn't even define a foliation. So the corresponding solutions wouldn't even have a preferred foliation, and it wouldn't be meaningful to be discussing this. And in this is what we showed. We showed that in Einstein ether theory, at least, the moment you give up spherical symmetry, then the ether prefers to develop vorticity, and you don't even have a preferred foliation anymore. Instead, in Horava gravity, the ether, if I can continue to use this terminology, is by definition hypersurface orthogonal, and hence there is always a preferred foliation. And you can find slowly, we look for slowly rotating black holes, and these slowly rotating black holes continue to have exactly the same structure as before. They continue to have this universal horizon. We also looked at lower dimensional, three-dimensional rotating black holes because it's simple with arbitrary rotation, and they still continue to have this structure. And we actually found something quite interesting there. We found three-dimensional black holes with de Sitter asymptotics, which do not exist in general relativity. And I'm mentioning that because we observed that in this kind of spacetimes, you can actually have a universal horizon outside the de Sitter horizon, which plays a kind of role of a cosmological horizon of the same nature. Essentially, there is a horizon that blocks things from coming in the same way that the de Sitter horizon separates the inner part from the rest of the universe. Right? So it might be that these universal horizons are actually, parallel killing horizons, at least in stationary settings, more than one would originally think. And to go further, one actually needs sort of a new toolkit, right? Because as I said in the very, very beginning of my talk, the causal structure of general relativity is global, and we understand horizons essentially in a global way with definitions that do not depend on symmetries, and that's what we would like to do here as well. So how do we define such a horizon in full generality? You might have noticed that so far the definition I gave you was somewhat operational. I told you, oh, it's an R equal constant surface, so it's a surface that doesn't actually reach infinity, and I know that I have to move in a certain direction when I leave that surface, so I can't actually go further out. But that's not a good enough sort of definition if I want to go outside spherical symmetry or almost spherical symmetry. Also, in general relativity, we don't only have global definitions, we also have local characterizations. Like if I give you a space-time and I tell you, is that a black hole, right? At least if the space-time is stationary, you can go and calculate and see if there is a killing horizon, and that would do the job. So that's in a sense, that was a sense the next order of business. How do I understand all of the heuristic things I told you in the beginning about the causality of these theories and about the existence of black holes in a more formal mathematical way? So setting aside what the theory is precisely, I obviously used Horava gravity as a characteristic example because I know it. But if I have a theory where causality is defined by a foliation, so the theory has a preferred foliation, and not by the metric, then how would I understand it mathematically? So first of all, I would like this foliation to be ordered, right, so that I know how time passes. But that's how essentially a set of space-like surfaces would actually make a space-time. I need to know how to order them, but I don't actually need to label them if I want to be general enough. I don't want to know that this is time t1 and this is time t equals 2 and so on and so forth. So I want to have an invariance like this. This is the most general thing I can think of. And then what I could do is, instead of characterizing, in general relativity, we say I have an event P and an event Q, and Q is in the future of P if there is a causal curve that connects P and Q that is future pointing from P to Q, right? You want to have something similar, but of course you don't want to call a causal curve a time-like or null, because it's not time-like and null curves that define causality here, right? Because as I said, causality is not defined by the metric. You could characterize curves as causal or acausal by the way they actually penetrate the leaves of the foliation. So imagine I have a stack of leaves here. I have a curve that penetrates a leaf here and another leaf there, marking events on them. And I know that this event is in the past of that event, essentially, if the tangent of that curve penetrates the leaf in a future pointing direction. I know that it's past directed if it penetrates the leaf in a past direction. So essentially what I can do is I can use the normal to the foliation, which is what I was calling before the ether in this setting, and the tangent to the curve, and by their dot product and the sign of their dot product, I can know if this is a future pointing curve or a past pointing curve, or if it actually lies fully on one single leaf, so it's actually not going north towards the future, north towards the past. And I can characterize it causal future-directed, causal past-directed, and sort of acausal, staying on a leaf in this way. And an interesting feature of this definition is that U is sort of naturally defined as a one form, and T is naturally defined as a vector. So I don't even need a metric to form this dot product, right? Which is consistent with the fact that the metric doesn't actually enter in the causal discussion at all. And once I have this kind of definition, then of course, if I have a point P in GR, that would be the future of P. And if I had a set of points, that would be the future of the set of points. Whereas here, I get exactly, the exact agreement with the heuristic definition I was saying. Everything in the north is in the future. Everything in the south is in the past, right? So I can define the future as all the set of events that can be reached by a future directed causal curve, and similarly from the past. I'm just replacing future and past. And why did I do that? I mean, it's obviously almost trivial, because if I want to define a black hole, right, in a global setting, in general relativity, we define black holes as the boundary of the past of some null infinity, right? And this is where I'm going. So then I need to understand, if I want to tell you, oh, things do not leave, a black hole is a part of the space-time where things do not travel outwards, right? They don't travel to infinity. I need to have the right infinity. And so if I go back to the space-time diagram, right, forget for the moment the foliation and all that, consider it as a standard Penrose diagram of Schwarzschild, right? This is the right infinity. The null infinities define the future and the past horizon, right? But these infinities are meaningless in a theory with infinite propagation, right? They're only special because I have a maximum speed, right? Because light defines essentially causality. If I have infinite propagation, there is nothing special about these infinities. It's actually this. Whoops. Sorry. It's actually this infinity here, the space-like infinity, that is the special one. So the right way to think of infinity here is I have a stack of leaves, right? Each leaf, if I follow it in a certain direction, I go infinitely far in space. So if I actually were to conformally compactify this leaf and add a point at infinity, map all of this infinity to a point, which is what we usually do in a four-dimensional space-time for spatial infinity, right? But if I do it on every three-dimensional leaf, and if I take every point in my manifold, which actually has such a point at infinity, for which I can actually follow that process and map infinity to a point, right? Then I can call all of this set of points this M, this bracketed M, where M is my manifold. And if I take all of these points and I stitch them together to a line, that essentially forms what I want to call my scry here, this type of infinity, which is actually a time-like line, effectively, right? And this scry is going to be the relevant infinity here. And with my notion of future and my notion of scry, I can actually define horizons in precisely the same way I do in GR, as the boundary of the past of scry and the boundary of the future of scry being the future and the past horizon, right? Which is essentially the ultimate point from which I can send information to the future or receive information from the future. From the boundary. And if I do this, if I do this, and I follow through the math, it turns out that this bracketed M that I defined is, in fact, the intersection between the future and the past of infinity, which is what we call in GR the domain of outer communication, where we can actually send freely information. And these horizons that I just defined are actually leaves. You can prove that they're leaves of the foliation themselves without assuming it, and that they're boundaries of M, as they should, as horizons should be. And the black hole is essentially what is sitting behind the future horizon, you could define a white hole what is sitting behind the past horizon. And a key point is, of course, that none of these surfaces actually reach my infinity exactly as it should, exactly as you saw before in that diagram, right? And so this is essentially the sort of global definition. A local characterization, which would be what parallels the characterization of a horizon in GR as a Killing horizon in stationary spacetimes, can be given here as well. So assume that your spacetime is stationary, that your metric is stationary. Then one can actually prove that a horizon of this type will be the locus of points where this will be satisfied, where chi is the Killing vector, u is the ether, the normal to the surface of the preferred foliation. So when this dot product vanishes without this vanishing, where this is just the acceleration of that vector, then these surfaces where this happens are automatically universal horizons with my previous definitions. And you can actually prove that. And the key point is essentially that this domain of outer this domain of outer communication that I mentioned before ends up coinciding with the maximal region in which the Killing vector is causal, is a causal vector. So so it doesn't lie on a leaf essentially, and you can actually prove that in the appropriate sense chi is unique. That no matter which Killing vector you choose, it will always follow this property. So if you have more Killing vectors and you can create combinations of different combinations of time-like Killing vectors, they will all have this property on the universal horizon. And this condition here that seems sort of an ad hoc condition, it turns out that this quantity A dot chi is actually constant. If it's not zero, it's actually constant throughout the universal horizon. And it plays pretty much the same role that surface gravity plays in a usual Killing horizon. This assumption in our theorem came as a sort of technical assumption, but the conjecture is that if A dot chi were zero, that would sort of be a degenerate horizon, right? The equivalent of a degenerate horizon. So there is a very clear analogy between the sort of chi square condition in general relativity and u dot chi equals zero condition here. Yeah, I'm almost done, yeah. Thanks. So assume now, so that sort of last thing I want to discuss is, okay, is that horizon sort of relevant for infrared phenomenology, right? It's sort of an interesting feature, of course, of how do you actually define this black hole in the full glory of a theory. But if you remember that this dispersion relation that the modified dispersion relation that I showed in the beginning with a k to the 4th term and potentially a k to the 6th or whatever, you can always say, oh, if I'm in low momenta, my theory will be almost relativistic, right? And perhaps I could, so the low momenta wouldn't really be aware of this sort of different causal structure and so on and so forth. So if I'm doing low energy phenomenology, would I actually ever probe all the way to that horizon? The real question translates to, can I ever find this horizon outside a conventional Killing horizon, right? Because if that were the case, I would actually, it would actually block more part of the space-time than I would probe with low momenta. Right? And in spherical symmetry, the answer to this question is obviously no. And the reason is, it's the very definition, right? For u dot chi to be zero, if chi is time-like asymptotically, u is always time-like because it's a normal to space-like surfaces, right? So this can only hold if chi has turned space-like. So in spherical symmetry, that always means that the horizon has formed. The sort of stationary Killing vector has turned from time-like to space-like, which means somewhere in between it has become null if you're in spherical symmetry. We know that that's not true with less symmetry. You have a stationary vector that goes from time-like to space-like. It its norm can become 0 at some point, but that surface doesn't have to be a null surface, and then I don't have a horizon, I just have an ergosphere, right? And that happens in the Kerr geometry. So there is there is a time-like vector that turns from time-like to space-like on an ergosphere. So you could start wondering, oh, could I actually find this universal horizon in an ergosphere and not behind a Killing horizon? Well, because of this statement that chi is essentially unique, which means I could actually choose any chi that I want, right? You get to the answer. You get the answer, which is no, because there is no chi essentially for which I couldn't apply this logic. So yeah, there could be some vector that this would happen, but there would be another time-like vector which would have actually turned null on a null surface. So if there is a Killing horizon, then the universal horizon lies behind it. But then, how do you know that there is a Killing horizon? How do I know I cannot find a space-time that has a universal horizon without a Killing horizon? And maybe I could see that in the sky somehow, right? So how do I know that there isn't a solution that, in terms of low momenta, would appear as a naked singularity, but it's actually only covered by a universal horizon? So that's what we sort of set out to prove, at least in this more limited setting of axisymmetry. So we assume that there is another Killing vector with a closed orbit, and what we showed is that if that second Killing vector is phi, then you can always define a vector v as this kind of combination of chi and phi in such a way that v dot phi is always 0, and then you're able to show that as long as these conditions hold, which I will explain in more detail in a moment, then you can use a variant of Carter's rigidity theorem to prove that v will always turn 0 on a null surface, and on that surface w will be a constant. So v will be a linear combination of two Killing vectors that becomes null on a null surface, and that means that there is a Killing horizon. And that will always happen outside the universal horizon, right? So that essentially proves that whenever there is a universal horizon and you have two Killing vectors, then there is always a Killing horizon cloaking it, right? And these conditions are kind of interesting. These are called circularity conditions for the two Killing vectors. They can also be written as conditions between chi, phi, and the Ricci tensor. And they're trivially satisfied in vacuum GR, right? And they're trivially satisfied in sort of electrovacuum GR and so on. But they're not even in full GR. Even in GR with matter, they're not always satisfied. So they're certainly not satisfied in Lorentz breaking theories in general, right? So when they're not satisfied, you can't even write the metric in the usual sort of axisymmetric form where the only non-diagonal component of diagonal component is the T phi one, right? So you expect sort of a large deviation from general relativity because you have a non-vanishing sort of term even in the best sort of gauge choice. But there might be that there are solutions that actually violate this term. So I can't say for sure. So let me close with that. So I want to, as a summary, let me just say that I think that black holes are of great interest in theories with Lorentz symmetry, precisely because Lorentz symmetry is so fundamental in defining what we mean by black hole in general relativity. So you'd expect also that deviations from Lorentz symmetry would be much more manifest in black holes than any other sort of space-time. I find it very intriguing that there is a non-trivial causal structure even in theories where you have infinite propagation speed, and that you can even define such a notion like the universal horizon. And of course, that's just the beginning. I mean, there are a lot of things we don't understand, like is this structure, this horizon stable, right? Will it actually form from collapse? Can I just collapse matter to form this black hole? Here we're just solving nice elliptic equations, right? Can I just evolve into this horizon? And these are things we're currently trying to understand. So thanks very much.
Yeah, time for a couple of questions.
So, can you define the hypersurface of
mean this one?
Yes. So
Okay.
as far as I understand, you take just ADM gravity because later you showed this L4 and L6. But
Yeah.
you said that you're neglecting them for the time being.
Yeah.
So you're just taking ADM coupled to ether, and then you're picking this hypersurface orthogonality condition, which to me looks like just fixing a particular gauge, right? So you're just taking one particular foliation, and then on the diagram with the universal horizon, you say that there is this universal horizon, but you probably said that, but it kind of escaped me. So if you could repeat an argument which shows that this horizon is actually a horizon and not just a point or a collection of points where your hypersurface condition breaks down, right? So that it's not a gauge singularity, or it's just not a place where your gauge breaks down, but actually a horizon. I mean, what is the physical significance of that? Because I'm asking this because in principle you could take Minkowski space and just choose a weird foliation which has some, in which the different leaves of that foliation just collapse in some sense, and you could say, well, you could see that my foliation doesn't propagate through the surface and there is a horizon. Right?
Your question is really, why is this foliation preferred? That is your question, I think, if I understand it right. Why can I just choose another foliation? What is special about this foliation? And there are actually two things that are special about the foliation, which so what makes a foliation preferred is, first of all, that I couldn't write these higher order terms in a meaningful way in any other foliation, because that would introduce higher order time derivatives, right? So, yeah, they're not there in the calculation, but they're there in the theory, right? So this is the first question, that if I want to consider, if I want to have infinite propagation there, I need to have these terms, and I can only write these terms in a foliation that I choose, right? So by writing the terms down, choosing the foliation in which I'm writing them down, and then I just neglect them for the calculation because they don't affect this geometry, I know that this is the preferred foliation. There is more to that, actually, which I didn't say for the interest of time, but it's a crucial feature of the specific theory, which is that it's a little bit of a cheat I did. So remember how I told you about the discontinuity when A goes to 0 here? That discontinuity is actually not present in the theory I'm considering, for a very simple reason, that the theory I'm considering even has infinite propagation speed even when A is 0, because it has a mode that is purely elliptic, right? So apart from the usual perturbations that satisfy sort of dispersion relation of this type, there is a mode that is purely elliptic, and it's hiding on the fact that you can see it already by the fact that I have a theory that is quadratic in the first derivatives of u, right? And then I'm changing u to write u as a derivative of t normalized appropriately, but now t is the fundamental field. So I actually have more than two derivatives of t in there, right? So you'd expect that this is a theory that has higher order time derivatives. It's actually, and that is true, except when I choose a specific foliation, in which foliation, essentially, one of these three derivatives in every occurrence is actually always a space derivative, and I don't have higher order equations. And that actually also, even at the low energy limit, picks up the foliation. So essentially, at the low energy limit, the theory, if you write it in any other foliation, it would practically not have positive energy, right? But if you choose the specific foliation, it becomes a sort of well-posed theory with propagating modes and an elliptic mode on the slices.
So can we have one more short question and short answer?
Yeah.
What happens to our local physics in the solar system? Is the preferred foliation in principle observable? But
Yeah.
we haven't been able to
So the preferred foliation or the preferred frame in Einstein theory is in principle observable through the ppn parameters that are called preferred frame parameters. So they come at like second order, first ppn order, one order above the Newtonian order, right? And that is one of the ways that one imposes constraints on the CIs or on these parameters here. So I mean the current limits of that is like about 10 to the minus 7. And you can just choose the four couplings in such a way that you're lying in the safe region.
Okay, I know there are more questions, but let's break off here, reserve them for lunch, and thank Thomas again.
Thank you.
continues on the theme of black and white holes. He is Louis Garay, sorry, I should say, from the Universidad Complutense in Madrid. Louis started in the distant days of the last century working on things like space transform and wormholes, especially ADS wormholes. He's extremely well known for his the master thesis on your minimum length in causal gravity, which has an amazing number of citations. I've cited it myself.
Thank you.
He then went on to work on analog systems of gravity, more specifically black holes, so acoustic black holes in both the Einstein condensates, and has, as part of that and extending that, investigated many classical and atomic aspects of black holes. And this is exactly brings me to the theme of today's talk. So I first thought it was quickly that we're bouncing towards a dark and compact end, but we are bounding towards it.
Well, it's like hoping.
You'll explain what it all means. So very good to have you here.
Okay. So thanks very much for inviting me to this conference, which is really promising and nice. So the bounding is actually the same thing as bouncing. It's just sort of hopping towards somewhere. And well, roughly the whole talk is going to be explained in the title, so that's fine. So let me start with a very kind of trivial introduction. First, in general relativity, we know that black holes present singularities and horizons. That is sort of a trivial statement. And we all know that quantum mechanics may well change this whole scenario because of mainly two reasons. And they might actually be connected. One of them is Hawking evaporation, and the other is the regularization of singularities. Let me go first to black hole evaporation. We know that black holes evaporate, emitting Hawking radiation. And the standard picture is that this evaporation takes place in terms of a very long-lived trapping horizons, instead of having event horizons, that is to say, the horizon ends up disappearing. But evaporation is an extremely long process. It takes a huge amount of years, like many, many times the age of the universe. So this means that any kind of experimental or observational test that we can make on the mechanisms that are actually driving all these quantum effects are essentially out of any possibility for us to do them. And also Hawking radiation is probably completely relevant from a astrophysical point of view. However, I should mention just in passing, although it is not related to this talk, that actually there are experiments in Bose-Einstein condensates in which they have already seen this kind of quantum fluctuations coming from horizons. So there exist many, many proposals for long-lived, regularly evaporating black holes. That is to say, many proposals for going from, instead of having this kind of diagram that we have had since the, I don't know, 20, well, actually more, 40 years almost, right? To this kind of diagram in which I haven't given here any details of what is in there, but obviously here we must have something that is regulating the singularity so that we end up with this kind of Penrose diagram. This is not surprising. I mean, the Penrose diagram is this one. I mean, we know the Penrose diagram is giving us just a very few information in this sense. There is no metric information there or anything. All I'm trying to say is that we are suppressing the singularity, regularizing it, and giving rise to some regular stuff. The first one actually that I know of dates back to the 80s by Bilkovsky and Frolov that provided this sort of regularly evaporating black holes for the first time. So the question that I want to ask here is this really the final stage of gravitational collapse? Is there any other possibility for regularly evaporating black holes? This brings me to another part of this issue, which is the regularization of singularities. We can regularize the singularity by means of some kind of violation of the energy conditions that may give rise to repulsive forces and that may actually stop the collapse, right? And probably not only stopping it, but if we have the matter coming inside, stopping and bouncing back. This is the kind of situation that I want to explore and to consider. If this happens, this would happen obviously at when quantum gravitational effects would take place, even though I'm not going to enter into the details of the unknown theory of ultraviolet gravity, but it would happen roughly at Planckian densities. And if you write down what means Planckian densities, this means Planckian curvatures, and this means that roughly that it happens at the radius of this size, in which we have here mass of the star over Planck mass to the 1/3. But if this situation is happening, we have two kind of contradictory processes here, two kind of dynamical agents playing a role here. On the one hand, we have matter that is going down, but at some point the star begins to grow. That is one of the competing processes. But the other, of course, is the geometrical one, in which we know that inside the horizon everything tends to shrink rather than to grow. So how can we make this compatible? So something that bounces back and is growing, but on the hand it cannot grow because geometry inside the horizon is telling you that it has to go inside. Can we make this thing compatible? Obviously, within general relativity, we can't. So we have to go beyond, obviously. This is where we are. So the way to do that is to introduce a transition layer in time in which we have modifications in the geometry that could be seen as violations of these energy conditions, and that could actually make this thing possible. So if we end up with a situation in which we have long-lived horizons, then the situation must change the interior geometry of the star instead of changing the outside. So that to say, we want to keep sort of long-lived horizons. This means that the geometrical description must dominate and the interior description must be subjugated to that. What we are trying to explore is the possibility that is happening. What is happening is precisely the other way around. It is just we try to say, well, we regularize the singularity and let's see what are the consequences that we have for the geometry, whatever they are. If we keep horizons, we keep horizons. If we have to kill them, we kill them. That is roughly the idea. But if we do that, we will find out that there is some kind of a shock wave that is coming from the violent bounce that is taking place in a very short time. So let's say the star goes like this, bounces in a very short time, and goes back. So here we need these energy violating situations, and this will generate some kind of very high curvature wave that is going towards the outside. I'll give you some more details about that. Okay, so that's the general picture that we are considering. In more detail, not much more detail, but in more detail, what we want to do is to make something bouncing. So we want to connect a black hole geometry with a white hole geometry. Okay, but we want to do that with a very short time. And the bounce takes place in a short time. If it takes place in a long time, we're back to the standard scenario in which we have these long-lived horizons. So if this situation is taking place, what we are considering is the possibility that we have the star, it collapses, bounces, and goes back. It goes back to the original situation. Well, it goes back to the original situation if we just take this pure dynamics, but in principle we are going to have all sorts of dissipation, just throwing matter outside, so that the star might be doing like that, going to an initial position that is not the initial position, but is sort of a smaller radius, and it may go like that, and ending up in a final situation, in a final stable configuration. Okay, so that is the idea. And what is the model that we are considering? I mean, there are not many details here, but they don't really matter. The picture that I'm going to show you afterwards is much more illustrative. So what we're going to do is we start considering Oppenheimer-Schneider collapse. But instead of using standard coordinates, I'm going to use Paine-Levé-Goldstone coordinates, in which I have here this B. This B is just a standard that I obtained from Spatial geometry. This V, I'm talking about that in a moment, and here I have another thing. So what are these things? The specific expressions are not relevant. The point is that I'm taking this V positive, and when this theta here is negative, this means that we have some kind of flow inwards. So this is what we describe in the black hole collapse. When this theta is positive, we are precisely having velocities, these flows coming outwards, and is describing the white hole situation. And and this theta, what it's doing is just interpolating between the black hole and the white hole, okay, with a size, within a time which I call time regulator. More illustrative is this picture. What we have is this is the whole space-time in these coordinates. So this part of inside here, inside this curve, which is the surface of the star, is the interior, obviously. So this part here is just the Schwarzschild metric. And what we can see is that the light cones here are changing. As I was saying, in t equals 0, we are changing from inwards flow to outwards flow in these coordinates. So we have a tilting of the light cone that is changing. Out here, it's okay. That is just a change of coordinates. It's very easy to see that it's just changing coordinates, and you can do a smooth overlap. But inside the horizon, the would-be horizon here, in r equal to m, here the change in the tilting of light cones from this to that is no longer a coordinate transformation. Actually, it's something which is very central. It's changing a black hole into a white hole. So that is something that cannot be done by a change of coordinates. So this cannot be carried out in general relativity. And in all of these bands that I'm going to talk a little bit more about it, it's just a transition region in which we are having something that goes beyond general relativity, and it's the one that is allowing us to interpolate a black hole to a white hole. Okay. So these numbers, Rm here, which is the this number here that I'm calling Rm, which is the maximum size in which I'm going to see non-trivial, non-relativistic effects, is a free parameter of the theory that, well, this is just a model. You have to put some parameters. And the other parameter is the total time that takes for the bounce to go. So this time, if I had, this is if we have a very short bounce, then this will be roughly twice the Oppenheimer-Schneider time. But if we have some delay because of the bounce, you will add it. If it's very small, it will be negligible. If it's large, you have to be careful. So that is the kind of geometry that I'm going to talk about. Details about this part, I'm going to give you, or some more explanations in a minute. So if this is taking place, what we see is that we no longer have long-lived trap regions. It's just transient. So we have the black hole, everything has to go inside, but at some point everything begins to go outside. So this is different. This geometry is clearly different, as seen from the outside. It's clearly different from the Schwarzschild one. Not in here. This is just Schwarzschild. But in here, there is this is very small dark triangle in which we have something that is highly non-general relativistic. There is something there that comes from quantum effects. Okay? And it is taking place in a low energy, in a low curvature region. Although these are not quantum effects generated in this region. But actually, this is just something that is coming from here and is propagated outwards. So what about this triangle, this triangular region that I've plotted? Triangular just because of the picture. What I really care is that it goes like a sort of, it gets narrower and narrower. So this region is the one that interpolates non-trivially between black holes and white hole, a black hole region and the white hole region, the one that allows me to tilt the light cones in regions in which this thing is not just a change of coordinates, it's really a change in the geometry. You can calculate how much, what is the Kretschmann curvature scalar. I'm doing this because obviously I want to compare with the Schwarzschild geometry, and there are the scalar curvature is 0, so I'm taking Riemann squared. So, but it doesn't matter. It's just curvature. What I'm in the kind of, I mean, the level of details that I'm giving is just curvature. I can compare what is the curvature of Schwarzschild metric as compared with the curvature generated by these fluctuations and or this non-trivial region. And what we see is that in the case that I'm taking that the star comes from infinity, this is a technical detail for the time being, we see first that it decreases with r. Okay? And of course, it depends also on the time that interpolation is needed. So this is why we see that this is kind of a wave that is getting diluted as it goes outside, as r grows. Okay? Here, I'm taking this T regularity constant in the sense that I'm taking this to infinity, so I didn't worry very much about that. But if you do the calculations carefully, and now you consider that really you have star that starts from a certain radius, goes down and back again to the initial position, you wouldn't want, or you don't expect that the curvature due to these effects would blow up. And if you do the calculations, what you find out is first that the transition region is shorter and shorter as the radius increase. That first comes from the calculation. And also, what you, in the end, what this means is that first, that this time, let me show you the picture, that this time gets shorter and shorter, and this picture shows, and also that the difference between the Kretschmann scalar of Schwarzschild and the Kretschmann scalar generated in these regions decrease with the radius. Okay, and eventually goes to 0, up to some radius, which is smaller than the initial radius of the star, and there everything gets Schwarzschild again. Okay. So how is this collapse seen by different observers? Well, the first observer I want to quickly analyze is an observer that is falling with a star. Let's say an observer that is going this way. How long does it take for this observer, the whole collapse, to go down and back again to the initial position if I'm ignoring dissipation? Well, to do that, all you have to do is to realize is that this kind of observer, for this kind of observer goes with the flow, and therefore this thing is 0, and so you get a time symmetric collapse. The amount of time that it takes for this, from this point of view, to go down, to collapse, is the same thing, is the same time that it takes to go up again. What is happening from the point of view of an observer that is located at the initial radius of the star? Again, for this observer, a stationary observer at this initial radius, V is 0, and dr, because dr is 0, and dr is 0 because it's constant, and v is 0 because there you have nothing, you are outside, so there is no flow at all. And so you end up seeing that you get exactly the same time for the collapse. Except that this guy is going to see the whole collapse as non-symmetric. Why? Because if the collapsing one is sending signals, he will see that first the signals go slower and slower and slower, and then when the white hole starts, it will come faster and faster and faster, compensating the time that it's taking slower and slower when it goes down with faster time, that the faster frequency that you have in the ticks when you are in the black hole, in the white hole situation. So one thing compensates for the other, and you get exactly the same time. Obviously, this is not what you will see. I already said it, but it doesn't mean that you are going to see it in a symmetric way. You have the same time, but the collapse is going to look much longer than the expansion. Okay? Sorry, I think I went. So the duration as seen by any of these observers is which one? Well, roughly the Oppenheimer-Schneider time, plus some corrections that if we are considering very fast bounces will be a tiny amount. So in practice, what you will see is just twice the Oppenheimer-Schneider collapse. which if you do calculations, for instance, for a neutron star, I mean 10 solar masses or something, it gives you kind of a millisecond. So it's really fast. Okay. So can we have, instead of short bounces, long bounces? Well, if you want to have something that it takes very long time as seen from the outside, we are saying that we need a very long time for the bounce to occur, a very long time in which the quantum effects are playing a role, because that is the only way of changing that. Okay? And what this in the end means, I already said, is somehow saying, well, I want to have long-lived horizons. So I have to adjust the way the singularity is regularized to that. While what we are trying to suggest is, okay, let's do the regulation of the singularity the way we find natural, in the sense that if we are at Planckian curvatures, the modification will be of Planckian order, and then this gives you a very short collapse, a very short bounce, instead of long bounces that come from requiring that you have long-lived horizons. So people, myself included, might worry about having quantum effects, quantum gravitational effects, in very low curvature regions, namely outside the horizon. But these are not quantum effects generated there. Actually, they are quantum effects that are being propagated because of this. It's very much like if I have a bomb somewhere, I will feel it here. But not because the bomb and the high energies given by the bomb take place here. It's just because they reach me in a kind of a wave. So this is the same kind of thing. It's not that the quantum effects are being generated here. They come from the high energy, from the high curvature region. And this is what I was trying to explain when I was giving you how the Kretschmann scalar goes down and so on. So I think I've said most of this. Perhaps I should mention that all this thing is self-consistent for short transients only, not for long ones, just because of this idea of an explosion taking place and propagating away. If this takes very long time, the whole thing changes. Okay, so this idea of having quantum effects that are outside the horizon, that are originated somewhere else, is self-consistent only for short ones, not for long ones. And also, I should mention that in all these issues, dynamics is important. Why am I saying this? Again, this is because all this is generated because of the dynamics of the collapse. If I had a stationary black hole, Schwarzschild black hole, eternal, I wouldn't see any of these things, because I'm not generating quantum effects outside. These are just propagated from the inside. So it comes from a dynamical point, from a dynamical process. But once we have described this model for the bounce, now we have another issue, and it is that we are connecting a black hole with a white hole. But it was shown in the 70s that white holes are unstable. So does this make any sense? And the answer is yes, obviously. Otherwise, I wouldn't be here telling you this. I would be here telling you something else. Let me give you a few details of why this is the case. So in principle, white holes are highly unstable to the accretion of very small amount of matters. This is what Early showed in the late 70s, actually. Well, not late, 74. And then other people developed during the 70s and 80s. So white holes turn into black holes very quickly. So that is the summary. And this means that our proposal of black holes turning white holes may also suffer this instability, and actually they do. What we have seen, what we have shown, is that transitions with very long with long bounces are pathologically unstable. This means that the tiniest accretion of matter destabilizes them, which means turn them into black holes, and we are back in the original situation in which we have long-lived horizons instead of having only short-lived trapping horizons, so that we have the whole bounce. While for short characteristic times, like the ones we are proposing, this instability does not play any role. Let me explain a little bit more. First, we need to know roughly, qualitatively, what is the process that is behind this instability. And the process is the following. We have white holes. White holes are attracting matter, but this matter cannot enter the white hole. So this means that we are accumulating matter that eventually would generate a black hole horizon, and this means that matter that is coming out is trapped in this horizon. But of course, this will depend on when the accretion of matter is taking place as compared with the coming of the matter from the white hole geometry. This means that I need two conditions. First, that white holes actually explode in the future. They are not eternal, but there is something dynamical that are exploding. And second, that they must be accreting matter for a sufficient long time so that they can actually create a black hole horizon because of the accumulation of matter that cannot enter the white hole horizon. So we need these two things. If these two things happen, then we will have an inhibition of the white hole explosion. In the case that Early was analyzing, he was considering primordial white holes, and so primordial white holes in the sense that we might have delayed portions of the Big Bang, and so we might have that sort of situation, and this would be something that actually looks like an explosion, but also that has been there for a long time accreting, and so they would have this sort of instability. In our situation, we have something similar. We have a white hole that is being created, but of course there will be matter coming down. So we have to analyze whether we have a stable situation or not. And I'm not discussing them here, but quantum mechanical instabilities, not because of classical accretion, but because of quantum fluctuations, behave very much with the same ideas and the same process. So I'm not insisting on that. To describe a little bit more about these instabilities, I'm going to just briefly give you the idea of what is happening with null shells. So we take a null shell of mass m that is collapsing and bouncing. We have this shell, but we also have some matter that is being accreted, and I'm going to call it delta m to the mass of another shell, null shell that is coming afterwards, just because of this accretion of matter. So what we want to know is whether this will destabilize the whole white hole expansion, and therefore we will end up with effectively with a black hole or not. So in terms of these null shells, it is quite clear what is happening. Again, if the shell that is exploding comes too soon as compared with the time that the white hole has had time to accrete this delta m, then it will go out before any horizon is formed, and we will have the white hole. But if the explosion takes place too late, so that the black hole horizon, because of the accreting matter, has been formed, then we will have the black hole and no white hole explosion. If you analyze what is the latest time that this bouncing shell is coming out as compared with the accretion, what you can see is first that for long transitions, I'm not giving you the calculations, but they're sort of simple. If you have long transitions, you can see that very small amounts of matter can trigger this instability. And actually, all you need is that very small, tiny, as you can see, amounts of matter are accreted, and during a very long period, essentially, or the whole time that just half the Oppenheimer-Snyder time. If you get that, what is happening is that actually the bouncing has been there too long, and by the time it comes out, the black hole horizon, because of the accreted matter, has already formed, despite the fact that it may be extremely small mass. But the horizon is already expanded a little bit, and it's formed there. While for short characteristic times, this is not the case. What you can calculate is what is the mass that has to be accreted so that this instability is triggered, and it's huge. As you can see, well, if you accrete 0.3 times the mass of your white hole, you're changing the whole thing. So, and also this should happen in a very fast time. That is essentially the crossing time of the horizon. So the short time bounces are very robust against this sort of instabilities, while the long time ones are not. And of course, there is a whole plethora of things in the middle. We haven't done any other calculation with non-null shells, but actually the whole analysis of white hole instabilities have been done with more general matter, and actually the whole picture doesn't change qualitatively. So we expect that the same situation will be happening here. Then, if all these things holds, we can see that there are like different channels for the decay of a black hole. The first one is the Hawking channel, let's call it this way, which is when a black hole becomes flat space because it evaporates completely at some point. But we know that the time needed to do that is proportional to the cube of its mass. So this is a very long process. This is what we were talking. The number that I was giving you before. There is another channel that has been proposed recently that I call it, well, actually it's Hagar and Rovelli's model, in which, again, they have a black hole turn into a white hole, but in terms of a very long time. And this very long time is shorter than the Hawking's one, but it goes with a square. And this is still very long. But this channel has some difficulties as far as a transition from black to white hole is concerned, because although obviously it is more efficient than the Hawking one because it has a shorter characteristic time, it is only valid in perfect vacuum. Because provided you have very small fluctuations, very small changes, and when I say very small, the calculations are really small. You can see that here there is this exponential, so this means that 1 CMV photon would do it, even much less. So this is why I was saying it's pathologically unstable. The instability will be triggered, and actually we will not be having this way of decay of black holes. You will go to the next one, which will be probably Hawking's, and that is much longer. And there's the other channel that we've been exploring here, which is the one that we were proposing, and this one is faster. Essentially, it takes the time for the black hole to become a white hole, roughly the crossing time, obviously, of the horizon, because we are dealing with very short bounces that actually do not contribute to that time in practice. And so this is stable, and this is obviously the most efficient because it's the quickest one. So if what we are sort of thinking about is about the possibility of considering these different channels as actually different processes that might be taken in black holes, and depending on which one is dominating or which one is present, we may have one or the other. More specifically, if there is no mechanism that may inhibit this fast transition from black to white holes, then we would have Hagar and Rovelli's one, but that is forbidden, so we would go to Hawking's radiation process. But if there is no mechanism that is that is not allowing that this sort of fast mechanism taking place, what we are suggesting is that this might be the way in which black holes decay from black hole to white hole. Up to now, all I've said is considering just a single. I've been talking about considering a single bounce that goes from initial radius to initial radius. But what happens always in collapse is that there are lots of matter that is coming out, there is dissipation, there are all sorts of things, so that probably what it will happen is that we have the star starts here, goes down, and comes back to a smaller radius. Okay? And there is a series of bounces that will end up where? Well, we have to consider different possibilities. But what I would like to insist or to mention is that first, all this process of bouncing and dissipation is not controlled by geometry. It's just physical processes like sending matter out, dissipation, all sort of things, but not really geometrical. And the final stage, and what is the final situation, is quite independent of this. Actually, it's what can hold something together as a star, rather than being anything, again, having to do with geometry or with the process of the collapse itself. So in this sort of scenarios, we are separating what is the final stage from the actual mechanism that is leading us to this final stage. So I want to use the next 5 minutes or so to provide a possibility for this final stage. So again, the question is, are evaporating black holes unavoidable? So to say, gravitational collapse in the sense that we understand it in the standard picture, unavoidable. If we are within general relativity, we know the answer. The answer is yes. There is no way we can overcome collapse. But in semi-classical gravity, taking into account back reaction, perhaps that is not the case. So we know that the Sweeney-Wald-Fooling theorem is telling us that the gravitational collapse will take place, and that in the sense that the energy momentum tensor cannot become infinite if you start from a Hadamard state, from a finite energy momentum tensor state initially, but it can be very large. It has to be finite, but it can be very large. And if it is very large, this means that we may have vacuum polarization that is actually preventing the collapse. When is this possible and when is this not? Well, if the collapse is essentially free-falling or is too fast, there is no way. The collapse takes, the building of energy momentum tensor with energy violations cannot be too large. But if you approach the horizon slower and slower, then you have time to build up all this polarization and might stop actually the collapse. This is the work that Carlos Barceló, Matt Visser, and Stefano Liberati did some time ago. So they showed that it was possible, that they opened that possibility at least. So if that is the case, in our proposal we have something very similar to that, because we start from something this big, and this does this, and goes smaller and smaller. But each time the star begins closer and closer to its Schwarzschild radius, and so it starts with slower and slower speed, and so you might have this sort of situation so that you would end up with something that is not actually a black hole, but something that is close to the horizon, hovering over it, but not actually being there. And it will be made of stuff, in the sense that it wouldn't be hollow like a black hole. It would be a very, very dense star. That is a possibility. So we wouldn't have any singularities, anything. We would have a very dense star, supported, for instance, by vacuum fluctuations, vacuum polarization, or whatever. I don't really know. And I wouldn't have any horizons, not anything. The final stage I'm talking about. Okay? And it would certainly not be hollow. It would be a dark star in this sense. However, black holes, general relativistic black holes, would still be a very good approximation to this. So we are thinking about is that these perfect mathematical horizons are a very nice, effective, and clean description of something that is much dirtier. Dirty in the sense of physical matter and having to deal with very complicated interactions and stuff. Okay? So I'm not talking anything much more. All I'm saying is that there might be also Hawking radiation, maybe not, but there are mechanisms that can give you something like Hawking radiation. It wouldn't be thermal, but because all the correlations would be there, of course, but it would look like Planckian. But this is a whole different story. My final words come to, okay, is this more of the same, so we can distinguish them from standard black holes, or we can? So, first, it's easy to imagine that the whole transient process until the stable final configuration has taken place, has been already established, seems to, or may well have very different distinct features than a collapse that goes like that. that goes without saying. As soon as you have some perturbation, some deviations from sphericity, you will have all sort of multipoles that will generate when they are when they go away. They will generate very different signatures. Okay, although we haven't studied that, this is just qualitative for the time being. But once they have settled, well, probably there is no observational way to distinguish them, in the sense that they will be very dark outside. The gravitational field will be like black holes, so it looks unlikely that there will be any difference. But what might mark a difference is elastic radar echoes. Because now we don't have a horizon. We have something that is very close to the horizon, but we have a surface. So this means that the time for a radar signal to go there and bounce is given by this quantity, where this r is the radius of the star. This r is the radius of the star, and this is the Schwarzschild radius. Okay? So, is this true? There is an R0 somewhere here. I missed things. Okay? There is an R0 here, and there is an R on the other side. So, anyway, it's just the time that it takes to go from here to the surface and back. So, if we take the radius of the surface equals to Rs, this becomes infinity. That we know. But if we take a finite, this is a silly number that I wrote there just for sake of illustration. If we imagine that the radius of the star is essentially its Schwarzschild radius except 10 to the minus 40 Planck's length, this is just a ridiculous number, and you would expect probably that the time for the radar echo to come back would be huge. Actually, it's not huge. It's 4 milliseconds. So what I'm saying is that these are stars in the proper sense, and even though the surface of the star might be very close to the horizon, the gravitational field outside is just Schwarzschild, so they would be probably undistinguishable from standard black holes. When you are doing something active, like sending a signal or something like that, you might be able to see them. So this is all I have to say. I want just to summarize very briefly the kind of topics that I've been talking about here. First is that black holes live too long. That is the summary. For me, that is a problem in the sense that if they live just like 10 to the 60 years, what kind of experimental analysis can I do of the physics that is behind evaporation or behind the regularization of singularities and so on? If the time scales are so large, I will not see anything. So for me, that's a problem. Maybe this is the way it is. What we are doing is just say, well, there's this other alternative, at least I can falsify it. Okay? So